My initial plan was to make another game that supported party play, but which is Snakes and Ladders. However, that took a little bit of a turn. It's a bit too complex to... Like, I wanted to be a simple tutorial for everything that you may need. It became a bit too complex, so instead I'm just going to go over the setups on their own, so not actually applied to a game. But I'm going to go over encoding data, decoding, Numpads and game codes, as well as pseudo-random number generator. So all things that you may need to make your own online multiplayer game, not necessarily with GBGShop's party mode, but with any third-party software to send messages with friends. Okay, so let's start off with encoding data. So first of all, the concept here is that, and this can be used either for multiplayer games or for game swaps, so this may come in handy for you if you want to make a game in which you want to send data from one game to another. But the idea is that we need... okay, if we want to send multiple amounts of data, we only have one number to do so. And we need to create such a number. So let's say, for instance, that we have a game where we need to roll 2 dice, and we don't just need the sum, we need to know exactly the 2 values and send them over. So we'd have 2 counters set to 1 through 6, okay, or let's say 0 through 6. So I'm going to refer to these counters as variables, okay? These are the this is the data that we want to send over. But of course we only have one number. So whatever will we do? Well, we can essentially merge them together in a very familiar way. Let's say I got a 4 and a 3, okay? Like very standard rolls. The way we can merge them together is just by doing something like this. Now, I wanted it to visualize better, but the idea is that I got a 4 and I got a 3, so if I were to send 43, I would have both of these informations in just one number. And they're also possible to decode, and we'll go over that. But how do we build 43, you may ask? Well, it's simple. We have the amount of tens, and we have the units. So the units are fine as they are, but the tens we need to, intuitively enough, multiply by 10. One way to do that without too many nodons is using a map nodon. So if you're not used to this one, I'm going to just set it up so it multiplies by 10, and intuitively how this map reads is that 0 maps to 0 and 1 maps to 10 and so on. So if you think about it, 0 multiplied by 10 is 0 and 1 multiplied by 10 is 10. Since maps are for linear operations and that includes multiplication, this map will essentially multiply any number by whatever this output range is. So if it was like this, I'd be multiplying by 189. Of course, that's not what I need, so we're going to set it back to 10. Okay, as you can see, we got 40, we got 3. We can sum them up together. Usually you're just going to not use a plus nodon and just put them both in the port that you need. But yeah, this is essentially the first step to sending over multiple amounts of data in the same number. And of course, this is a modular kind of thing. If you need 3 digits, you can just multiply by 100 then. The way I'm choosing these, of course, is that I know that these are dice rolls, so they will never go over 9. In fact, they will never go over 6 to begin with. So I know that decimal digits are more than enough to carry the data and make sure that they don't inflict with each other. Okay. So, okay, and of course if I had more dice, again, I'd be multiplying by the next power of 10. So here I multiply by 10, then 100, then 1000. Okay, so we got our data. right now I don't want to mask it in any way. We're getting to that point later. I want to make sure that this is as readable and understandable as possible before we get into the more advanced things to kind of mask the data. But once we have 43, how do we decode it exactly? Well, one way to do that will be to use counters to get the remainders of a division by 10 or by 100, depending on how much higher you go. Right here we only have 2 digits, so we don't have to worry about much, but after I may add more data just to show you how it would work. So right here I have a counter set to unchanged from 0 with range 0 to 10 and set to loop. So actually, before I explain what it does, let's just wire them together and see what happens. Remember, this is 43. 3. Now this is the units, so this counter gets the units. The way that it works is that it actually counts up to 43, but every time it gets to 10, it loops back to 0. So it counts 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 is too big, so it goes back to 0. Notice that 10 and 0 share the same units, so it loops back perfectly and gives us the correct units. So 43 outputs 3, of course. If this was another number, let's say 5 for instance, this will also change accordingly. So now we're working with 45. Okay, what about the tens? Now, we could just use what we just got, but there is a better way without actually looking at what we did here, and that's useful because otherwise you need to like time them correctly and make sure that you got the value here, then you can actually check for the tens. Well, what we can do is just do the opposite of what we did here. So here we had multiplied by 10. The opposite would be dividing by 10, and similarly we just need to have an opposite looking map. So 10 on the input range instead, and 1 on the output range. Intuitively again, 0 divided by 10 is 0, and 10 divided by 10 is 1. So of course here we're not really getting 4, we're getting 4.5. We need to get rid of that 0.5. Now, okay, sorry for the brief interruption, but I go on a wild tangent where I don't know what I'm doing. So essentially what you'll need is, remember the counter that we used underneath for the units? We can just use something like that in a setup that looks like this. So as you can see, we have the map that we just used to divide by 10, and then the counter that will take the remainder. Of course, in this case, the remainder is just the number without the decimal stuff. The only thing that you need to be careful about is the fact that the counter doesn't always truncate the number. Most of the time it will, but if you have a value between 0 and 1, then it will round up, which is not what you want. If you want to detect a 0, it can't, unless you add a little bit more code to make sure that it works flawlessly every time. Again, I said it's modular. What I meant by that is that you can extend it. So if you have more data, let's say we have 3 dice for some reason. Let's also give it, I don't know, 2. I don't know, unlucky shot. Of course we can't use 10 again because 10 was already taken, and we don't want to deal with those first 2 digits. So we need to work with the 3rd digit that doesn't interfere. That's the hundreds. Okay, and then you just add it up. And showing off that you can add the things by just putting them in the same port, this should be 245. So you've seen how to encode multiple pieces of data into the same number, and how to reinterpret the number in a modular fashion. Actually, I could probably do better over here as well. So using what we learned so far, let's ignore that. Here we first divide by 10 and then take the remainder. If we were to divide by 100 then, so let's do this, 100, and then take the remainder, we should still get 2. And also do it in one less node on. And not only we did in one less node on, we are now allowing, first of all, you better see how modular it is, right? how similar these cells look. Other than the first one, and again, the first one could have a map, it's just not needed. It's not needed to divide by 1 because it's the same. But for everything else, you keep dividing by the next power of 10 and then taking the remainder. So this is a modular setup that can go on and on till your heart's content, or till the node on limit and other limits of Game Builder Garage. And this same thing, actually, as you can see, very modular. We have the data, we have the multiplication, and then we add it all together. So hopefully this gives you a good understanding on how encoding and decoding works. Again, the encoding is just take the different pieces of data, put them all together in a number. In this case, it's a very readable number, but we'll get to making it less readable later. Okay, you put them all together in a big number, and then that big number is divided in its smaller parts, thanks to these setups. Let's take a look at something a little different. So right here, we've seen how we decode, but how will you input the code? Again, Numpads are not something that you see often, but they're not that hard to make. First of all, we'll work on the logic. We'll still keep this piece of code because it's useful to, you know, to have around. But let's just make a small visualizer with the 2D marker, shall we? So we're not going to make the UI in-game right now, at least, but I want to make a way for people to visualize what will be going on in an actual Numpad, which can be made in many different ways. So how do we input the numbers? We will need some stick nodons or buttons, whichever you prefer. After all, we only need digital outputs to increase counters. Okay, so I show the position and then show how you actually get the values and create the code that is then decoded. So let's see something like that, and then we copy it and use it for up-down movement. Okay, then we have counters. There we go. Okay, so really what we're working is the positions. So we want to move on the numpad, and then we're going to transform the position very easily into the actual number that we want to send. Again, it may sound scary, but it's not that bad. So left right should count up. So okay. Oh, also I should set to change from 0 and have it loop between 1 and 3. Actually no, 1 and 4, because 4 doesn't count but 3 does. So it starts at 1, which is good for me, and then it goes up to 3 until it loops back if you try to go over again. While this one starts at 0 actually, and it goes up to 4, so 0, 1, 2, and then 3 will be our jolly, let's say, our joker. There's a reason why. So I'm going to use a few maps here just so I can display what's going on through the map. Sorry, through the... I guess this is kind of a map, but like not the map I was talking about. Through the marker node. So again, we see 1 through 3 should go 0 to 1. And here we actually need an inverse map, because I want the thing to be higher when it's at 0 and lower when it's at 1. So again, this goes 0 through 3, but we want the inverse map. And there we go. So, okay, I mapped it a bit wrong. Let me... There we go. Okay, so we're not using this column, but as you can see, when I move right, it moves to the center. When I move left, it moves over here because it loops. And when I move down, okay, wait, that's moving out. Okay, got it. I think it's like this. Yep. So, okay, up, down actually goes into the down port of the counter. That's always confusing. So, if I move up, I'm actually moving down here. And if I move down, I move down 1. Okay, so how do we build a number, you may ask? Now the main issue here, I may want to change to buttons because this is a bit tough to work on, because every time I move, when I stop moving, then it resets. So remember what we did with the sticks. I'm just going to redo it with buttons. But so in theory this time I should be able to move around. So if I click right, it moves over right, then again, and then I loop. So as you can see, I have full freedom. And oh, okay, I guess up is not really something I should click. But if I were to click it, it would go back up. So right now I'm just clicking down, and as you can see, it loops back. We can use these two counters together to create the actual value that we're looking for. How? Well, this one's fine as it is. We need another map. We need another map for this counter right here. Essentially, we're multiplying that counter by 3. Okay, so again, as we've seen before, 0, 1, 0, 3 is a map that multiplies by 3, just like the ones before multiplied by 10 or 100. And now, I'm gonna display it using a number object so you can see it clearly. And I don't need 2 digits, I only need 1. Let's also get rid of all of these. Again, this is only in the programming screen, but you'll see what I mean. So, if I sum these two together, so that this counter over here and that map, I will actually get the correct number over here. So as you can see, I'm on 1, 2, 3, back to 1. I go down and it's 4. Why? It's taking this 1, multiplying it by 3 and adding 1 again. So 3 plus 1 is 4. 5, 6, 7, 8, 9. Now the problem is that right here, it goes up 9, 10, it will be 9, 10, 11. We want to avoid this. We actually want this to be 0, and we don't need these two spots. Okay, there is one way to work around this. We can use a multiply. Where is it? Where is it? Over here. So we can actually multiply by a value, or rather a logic value, which is either 1 or 0. So if you send this like this, of course it's multiplying by 0, so nothing happens. But by looking at this value, we know how far down we are. So 0 and 1 behave as they should. Also 2. 3 is bad. So when it's at 3, we should multiply by 0. So tell him, hey, force this to be 0. Otherwise, we should send 1. So now we're going to see another use of the map, this time by enabling the range. So we see now the linear operation works. Let's first work on the output range. We need either 0 or 1, that's clear. We said that 0, 1 and 2 are fine, but 3 isn't. So 3 and 2 are our upper and lower range for sure, because one of them should work and the other one shouldn't. Next, we want to map 2 to 1 and 3 to 0. So see how I'm doing the cross thing? That means that I need an inverse mapping. Next, enable range. See how it changed from 3 to 1. Enable range makes sure that only values in between 0 and 1 in this case are outputted. So if the map were to give you a value using its function, its built-in function, if it were to give you something outside of the range 0, 1, it rolls it back to the closest value that's in range. So if I go to 2, it goes back to 1. If I go up to 1000, it still is 1. If I go in the negatives, it will be 0. And of course, anything in between is handled just how a map node would handle it, except that, of course, in this case, the input is never going to be a number between 2 and 3. It's either going to be 0, 1, 2, or 3, so we're never going to say anything in the middle. But if we then map it here, as you can see, 1, 2, 3, 6, 5, 4, 7, 8, 9, 0. The lowest row is hard-coded to be 0. All of it. Now you can do a little bit more, you know, forcing to make sure that it stays in the middle, even though I'm coming from the left or from the right. but I'm not going to do that right now. The important thing is that we got the logic done, mostly. Okay. Oh, it's also moving the cursor around. Interesting. But yeah, hopefully you understand how this thing works now, and even if you don't, you have this code as reference. But again, this is a pretty simple thing. How do we now transform the values that I'm getting here into a full-on number to be decoded? I think this is the foremost toughest part, because I think the Numpad, once you make one, I'd say it's like riding a bike. You either just do it the same or even get better at it. Like, really, it just takes a little bit of trial and error, not much. But here, let's say that we know it's a 3-digit number, so we know it's 100, then 1000. Sorry, I'm going the wrong direction. It's 100, then tens, and then units. So we know for sure that we're starting at 100. I'm just gonna set to the max and then set the range to 100. Also unchanged from 0. So we're starting at 100. Remember what we did over here? Multiplying by 100, multiplying by 10, multiplying by nothing, because multiplying by 1 doesn't do anything. We're doing the same thing here, one at a time. So this counter tells us, hey, the next number needs to be multiplied by 100. And once you select that, it's going to change to 10, and then it's going to change to 1. I'm going to show you a not an efficient method to do that. But first of all, let's get 1 digit in, and then we'll figure out how to change this counter, okay? So what should be the thing that the actually, I need another oops. I need another counter to keep track of what we did, of what digits we have so far. So as you can see right now, they're all 0 because I'm not sending anything. But I need another counter over here that starts at 0. That's important. This is the code that we're inputting in. Also, I'd say no limit. Everything else should take care of the limits. I think no limit makes sure that it's always compatible again. Okay, so this is the code that we're inputting, and this is how we're inputting. So 100 and the number for sure. So we need the number that was over here first through the number node on. Now we're actually sending it over here. But we don't want to send it right away now, do we? We need another multiply node on to confirm our choice, to confirm, yes, we want this number, you can send it over. That could be the A button. So we select our number on the numpad and then we press A. Now button press, A. Actually, I'm going to have it up here. I want to keep the code clean. I'm going to share this thing with comments, so that you can revisit the code without necessarily checking the video, or check the code more in detail, because I may miss some things here and there. So if you want to make sure that you got it right, I will share the code after I'm done here. But yeah, as you can see now, it's sending nothing. If I press A, I was onto 1, so it sends 1. If I shift, you can see the thing moving down there. Now I'm onto 2. Actually, wait. Okay, now it's reset. Now that I'm onto 3 and I press A, it's 300. So it's doing it correctly. Now we want to make sure, and if you don't trust it, I can also go down here and then I'll do 6. As you can see, 600. We want to make it so that every time we press A, this thing changes to the next one. This can actually be done with a multiply again and a map, I'd say. Actually, the multiply, no, that's not the same. We need to take the current value of the counter, okay, and actually we're going to map it first and then to the times. So I'm going to need a map. Okay. Just so you follow me, here's the thing. There is a pattern here. If we're using the, like a fixed base. Right here we're using base 10. So let's say we start at 100. The next one is 10, which is 90 less than 100. After 10 we go back to 1, which is 9 less than 10. So 90, 9. They all have in common that we multiply something by 9. What did we multiply by 9? Something that has to do with the current value. Of course, it's not 100 times 9, because that would be 900. That's a bit too much. We need 90. So this map is going to both divide and then multiply and then subtract. So it's going to do a lot of things. Let's figure them out one at a time. So first let's connect so we get actually 100 here. This is the initial map. So we said that we want to divide by 10. Okay. Or actually, we can do something smarter. Use this as a map node on. So 100 we need to turn into minus 90. Okay. Just put down 100 and then put negative 90 over here. Okay, so what's wrong right here? Well, crisscross applesauce, we need this. I'm not sure this works. Because again, I don't think 0 should be mapped to 0, but that doesn't matter, because just like we know what 100 should be mapped to, we also know what 10 should be mapped to, right? 10 should be mapped to minus 9. So let's do that for this value. As long as we have two examples, we can put the examples in the map node on, and that will guarantee that it works. So we know 100 goes to negative 90. Now let's make sure that 10 goes to negative 9. And again we want... oh, oops. That's not the one I wanted to fiddle around with. Just do it here. Negative 9. Make sure that it's not enabled, the range. The range should not be enabled. This should work regardless. So right now it's getting 100, negative 90, 10, negative 9. Just if you were skeptical, I can try this out with 1000. 1000 should give us negative 900. So this could be our outside range test. Ignore that, the maximum is 1000 anyways. So 1000 connected to the map, we expect negative 900. And there it is. Okay, so what we're doing now is wiring this map to the counter, to the calculator node on, that checks whether we pressed A or not. Okay, so A is either 0 or 1. Oops, I didn't mean to connect it like that. A is either 0 or 1, so 0 sends nothing and 1 sends exactly what was in this first port. We send it over to count up in this case. We have the negative number. Another thing about it, I could have just done something simpler with the map, because there is a countdown port on the counter. I may have a simpler version in the final code, but I guess this was a good lesson on how you can use map node-ons for more complicated things. So when I press A right now, let's see if it works without looking too much at this. Let's see if it works by taking a look at this counter and what I'm doing over here with the numpad. So let's say we want to input what we had before. That will be 2, 4, 5. So 2, 4. Okay, it sent 5. Oh no, it sent 5 and 6 because these are the 5 and 6 positions. Okay, let's try that again. This time imagining the correct numpad. So 2 is over here, 4 is over here, and then 5. Now, if you keep pressing A, nothing will happen because you're trying to send something that's too small. Basically, this counter will be 0, so you'd be sending nothing, because this multiply node sends 0, this sends 0, and this sends 0. So after you're done with the units, no matter what you click, it will not change the number. I clicked something else and moved the programming screen. Ignore that. Like, yeah. 3, 9, 7. Yeah. Of course, we can try the 0. Don't forget the 0, everyone. 2, 0. Of course, you can't see that it happened, but if I were to press 8 now, it should be in the units. And so is that. Okay, so this is how you'd make a numpad. Of course, then you'd have to actually make it, you know, just not marker based. You need to have something in the game that shows what number you're selecting. That's not really something I want to go over right now. It's simpler than the logic that I'm showing over here. All right, I haven't showed the best part. Let's send 2, 4, 5 blind. Hopefully I remember. So left A, down left. Sorry, right. 4. Okay, and 5. See, this is what I was talking about. This didn't work entirely. It got 2, but then it didn't get these other 2. Why? Because I'm building the number as I'm going, which is fine. I want to build the number as I'm going, but I don't want to send it as long as I'm not done. So we're going to add that. Actually, I could just use this plus node on that's not really useful for anything, and turn it into a times node on instead. So what piece of logic could we use to make sure that we got to the final part? Remember how I said that when we're done, this becomes 0? Well, we can use a not node on to check for that. So we can have a not node on connected to that counter, and that will send the number over. So right now, even if I'm inputting, I'm staying over here so you can see this counter change, and this counter stay the same because this will stay at 0. So as I'm inputting the number, nothing happens. 4. But when I send the 5 now, or actually let's do something different, send 6. As you can see, the not node on activated, this line has become powered. And we're sending the number, the finished number, right now. 2, 4, 6. I got all the digits correct. So yeah, this is how you'd make a numpad, this is how you make a decoder, and of course this is how you would make an encoder. In this case, we've got the numpad over here, but the reason you'd need an encoder is because not everyone is going to be inputting the codes. Some players are going to create the codes, and the way you create the codes is by having encoders like this. Like, in this case, the third-party thing is the numpad, pretty much. Because one player creates the code, you send it over, and then the other folks have to use the numpad to recreate that code, which is then decoded, and then everyone is, again, on the same page. And this theme of being on the same page in a multiplayer game is vital. And here's my final thing for today. A pseudo-random number generator. And I know what you're thinking. Dalmot, we already have that. It's called a random node-on. Well, the random node-on is a bit too good. You know, it's very good at doing what it advertised to do. That is, doing random stuff. That means that if you activate it on different systems, even though it's the same game, it's going to give us a different value. Let's briefly go over what it does so you can understand what we are going to do next. So as you can see, this is a random node on, let's say 7. What it does is that depending on this, we're only going to look at unchanged from 0. When it receives a value different than 0 on its upper port, it's going to generate a number between 1 and the range specified over here. In this case, let's do 7. There's a reason for that. Even though it's going to be a small random number generator, you're going to know how it works, and and this specific setup could be very useful for a party play game, actually. But yeah, actually, let's showcase it. Let's get a button. Then we haven't used that. Let's use B. And if I press B, I generate a random number between 1 and 7. So 6, 3, 7. Okay, so I guess actually what I needed was 6, not 7. I'm going a bit too fast. I already have my head on the pride next. As you can see, it's a bit too good. I'm actually pressing sometimes the button. As you can see, it didn't change. It just generated 4 again. And yeah, depending on I don't know, pretty much anything, the output will change. The problem is that since we want every player to be on the same page, we want the random number to always do the same thing. That's not really something that we can set the random number to do. The random node on it doesn't have like a seed port to set a seed. But we can make our own random number generator. And here is how we're going to do it. So, it's not the only way to make a pseudo-random number generator. It's just the simplest setup I came up with. And by I came up with, I mean knowing how it should work mathematically. I'm just going to remake that. So, first of all, we choose the range over here. It should be 0 to a prime number. Yes, this is one of the limitations. We need a prime number over here. I chose 7 because it's, you know, pretty small number. We can instantly verify if it's working or not. Also, set it to unchanged from 0 and it starts at 0. Okay, it's going to be the random number generator. Next, we're going to need, yes, I know I said we weren't going to use it, but either a random node on or something connected to the upper port that sets the seed. Now, there are two ways you could set the seed. You can either have a master player, let's say player 1, create the seed using the random node on, and then send it over to other people using a code system that we've looked at over here. So, let's say player 1 generates a random number, which is used as the seed. You need to send that seed over to other players. So you create a code, you encode the seed, and send it over the other players. The other players will input the code, get back the seed, and then everyone's on the same page. Okay. Again, I'm going to need from 1 to 6 here. This is going to be the seed. Next, we need a way to get the next random number, and that will have to do with this countdown port, because realistically speaking, this may or may not be powered. So one thing we can do to avoid having problems with this is just using the other port, which ignores whether the already used up port is powered or not. Okay, let's go over this. So, let's see if I remember correctly. I'm definitely going to need a map. Now, what this map does is that it multiplies the current number by another prime number that's between 1 and 7 in this case. So, okay, let's say, I don't know, let's try 3. Okay, there is a fine prime number. It may not work as we want it to, but we'll get over that when we get there. So, next up, we're going to need a times node on. This is again a logic type thing. We want to send 0 when nothing's going on, and when we want to pull a new number, we're going to send a signal equal to 1 here, and that will be sent over to the counter. Not gonna lie, I'm pretty sure I'm done here. Pretty sure the generator is up. Now, let's see if it works correctly or not. Now, there are a few things we need to check to make sure that it works correctly. So let's summon back the B button. We missed you, buddy. And go over here. So let's see what happens if... Oh, right, I need a random seed. Yeah, nothing will happen if I press B right now, because I'd be just sending 0 over and over. We actually need a seed. Let's go with, I don't know, L for this. So when I press L, and I'll only press this once, again, the seed should only be used once, okay? So I press L and I get 5. Okay, let's see. If I press B, I should get the next random number, which is 4. Let's press it again. 6. Okay, good. 2. 3. 1, and then it should go back to the first one, which was it 5? Yeah, it was 5. So what are the characteristics of the... Actually, I should, since I got lucky, I should show what happens when you don't use a good prime number. Let's say I chose 5 instead. So let's see if this works. 3, 2, 6. No, this also works. 5, 1, 3. They seriously get it depends on the seed. Okay, let's get a seed we've never seen before. Seed we've never seen before. Are you kidding me? Are you kidding me? Holy smokes! Give me a different. Oh, something else. Okay, thank you. 2, 6, 4, 5, 1, 3. No, this seems to work. Okay, I guess I got lucky. Not all prime numbers are going to work. Let's keep 5 since it seems to work. Again, what do I mean by it may not work? Sometimes you may get a sequence that's very short and doesn't actually go through all the numbers. Something that loops early, essentially. In that case, you're gonna need to fiddle around with this prime number until you find something that goes on for a long time. Now, you may be wondering, why do I need something so small? Realistically, you're not going to need a pseudo-random number generator with such a small scale. However, what this is useful for is that it does generate a random sequence. A randomized sequence that goes through every number in the range and then repeats. This may sound familiar because it can be used for a turn order system. If everyone's on the same seed, but you want a randomized turn order, you can just use this. It loops back, so first, I don't know, let's see, let's read it. So first it's player 1, player 3, player 2, player 6, player 4, player 5. We ran out of players. It just loops back. It's the same exact sequence as before, because of course it's an algorithm, it's not really, again, it's a pseudo-random number generator. The idea is that they're random enough, but of course it feels more random the bigger the range is. But with smaller ranges you can still use this for, again, in this case a turn order. You can use it for other stuff as well. Again, I wouldn't recommend using this for a dice roll because it is a sequence that repeats. Once you've seen the sequence, you know what to expect. But for a turn order, that's exactly what you want. So do what you will with this. If you want an actual random filling thing, you're going to need a bigger range. Find a good prime number that actually loops properly. This may take some extra code to check whether the prime number you got is good or not. But other than that, you should be fine. Okay. So this is the random number generator, the pseudo-random number generator, this decoder, the Numpad logic, which is actually like the most stuff, and the encoder. I'm trying to think, okay, we're on to the a bit more advanced stuff, okay? So right here we created a code that's, yes, it's easy to read. However, the problem is exactly that, it's easy to read. People are going to easily find a workaround, input their own codes, and be done with this. So and like ruin it for everybody, because then they input a different code, meaning they're not synchronized anymore and they're cheating. So we don't want that. There are a few things we can do to prevent that. First of all, it doesn't have to be times 10. Sure, it has to be times 10 over here because we're inputting a code and we want the number that we're inputting to reflect that, right? The code itself. But then the decoder can do whatever it wants, and same thing for the encoder. As long as the encoder and decoder are doing the same thing, this should turn out for the best. So, for instance, 5 is fine. How do we know what to use rather than 10? Well, it's simple. We know that the values can only go from 1 to 6. Actually, let's keep it 0 through 6, so it's a bit easier, even though 0 cannot happen on the dice roll. Well, that means that 7 can never appear. So what happens if here we multiply by 7, you may ask? Well, the thing is that we have now discovered a different base. Let's ignore that for a little bit, but we'll get to that. We discovered a base that's not base 10. In this case, we have base 7. Base 7 means that we only have 7 symbols for each digit. In base 10, we have 10 symbols. They go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I named 10 symbols. In base 7, you only go 0 through 6, and then you loop back to 0. It means that you get to 10, not really 10, but like 1, 0 in base 7 a bit earlier than you get there in base 10. And 1, 0 in this world would mean 7. But that doesn't matter because right here we're still visualizing this as a base 10 number. So while this can be a bit confusing, I can assure you that we are not losing in fact data. I'm going to use a plus here so you can see what the full number looks like. So we have 4 times 7, 28. So we're using the second digit in base 7. And then we're sending 5, which is already units in base 7. 33. So 33 holds the same information that 45 did earlier, as long as we also modify the decoder afterwards. And yes, so this carries both 4 and 5. What if we want to carry more? What's next? I can just do map 7 here. This was 100, so what's next? Well, 100 will be 10 squared. It was the next power of 10. So what we need is the next power of 7 in this case. That will be 49. 7 squared is 49. And I can actually prove it to you by changing this value. See how we got to 33. Now, the problem with 49 is that you may think, wait, doesn't that interfere with this? We're pretty close to 49 already, right? We're pretty close. Well, see what happens when I change this to its maximum values. Both this one and the next one. So we got 66 in base 7. And that should be 48. See, it's one less than 49. 49 is the next one. And this is a thing that you can use for mixed bases as well. That's a bit too advanced, but this is like your introduction to it. Here we had 6. If this was 1, we'd be sending 7. We send 1 more than the maximum value of the previous digits. The maximum values that the units can provide is 6. The maximum values that these 2 digits can provide is 48. So we do 49 next. And that ensures that we don't interfere with anything. Okay, so let's go back to 4 and 5, because that was our initial thing. So 4, 5, and 2 should be still 2. Okay, multiply by 49, which we see is fine, and we send it. 131. Okay, of course, this is how you can encode using a different base than 10, but the thing that you get is still a base 10 number that you can send over as a code. This is of course way harder to read. I can't read from this as a human that I rolled a 2, a 4 and a 5. Okay, let's see how it would work here. So of course if I were to send as of now 131, 1, 3 and 1, it still decodes them as before, but this is not what we want. We want what we had over there, which was 2, 4, 5. So we don't need to change anything in Numpad. We only need to change the decoder. So right here is the first thing. We did the remainder 10, but we actually need remainder 7, because now we're working in base 7. So the base that you're working on determines the range of these counters that get the remainders. So this will also be different. Okay, and 7 over here. Again, here we were dividing by 10 because we were in base 10. Naturally, this time we will be dividing by 7. And same thing over here. We were dividing by 100 because it was the next power of 10. But what's the next power of 7? It's 49. So again, modular things that if I input 131 again this time, hopefully I didn't make any mistakes. 1, 3, 1. Look at this. 2, 4, 5. Exactly what we started with. So again, this is how you'd make a more actually a more compact system, because before we were wasting digits. We were using decimal digits even though we were never going to get 7, 8 or 9 in there. Or 0. We're still wasting the 0, but that's besides the point. We still compacted it quite a bit. Okay, but people can still cheat, right? As of now, any code is fair play, right? Any code is fair game, and they'll just get different values. How can we make a system that makes sure that the the code you input is correct. There are two ways I can think of. One that you can only use, actually, if you have multiple data. That's why I started with multiple data over here. That would be a checksum. The concept of a checksum is that you're going to have an extra digit over here. And now I'm in a pickle because I don't remember what 7 to the third power is. I think it's 343? So I'll go with that. Actually, I can check. Right. If you don't know the number, don't fret. Just set every previous digit to the maximum possible value and then go +1. So assuming I'm correct about 343 being 7 to the third, this should be 342 on the plus node. Okay, I was correct. So yeah, next one is 343. What I was saying, yes, checksum. So you take the numbers, sum them all up together in another counter that still loops back. So it's not like it's not like a absolutely like it's not like a perfect system, but it's still good enough to, you know, add a bit more data to check whether the thing you input is even correct in the first place or not. So you'd have a system where you start with a counter set from set to 0. Imagine me doing this. I'd be summing up all of these values and sending them over here to, you know, add on to the code. The code will probably become 4 digits, and fear not, you can just change this to 1000 and you'll be good to go. Now, how will it work here? Well, simple. You'd have another setup like this to get the 4th digit, and then, of course, remember that this is not 49, but it's 343 in this case. Again, I'm using base 7 in this case. You can use whichever base suits you, as long as every digit here does not go over that base. You should find the smallest base that suits that can suit every piece of data. Either way, this will be the checksum. How does the checksum work? Well, remember that we got the checksum by checking these 3, right? So once you encoded these, you can actually calculate the checksum again, and then just compare it to the 4th digit. And if they're the same, that must mean that, not that it's correct necessarily, but that it's one correct code. Of course, the probability of you getting a correct code now is way lower, because there are many codes in there that are junk codes, let's say. Codes that have a checksum that doesn't work. That doesn't actually equal the calculated checksum from these 3 digits. So we add data, but we really don't. But again, the added data we can use to verify that the code you input is correct or not, and then you'll have your game do whatever suits the game best, depending on what you're doing. If you get an incorrect code, most realistically, you're just going to say invalid code and then reset the thing and have the player send another code in. Another way, actually, this is very interesting now. What if, for instance, in Snakes and Ladders, you only need to send the 1 dice roll? Remember the random number generator? Now, I use that for a turn order, which is fine. You can have more than one of these. You can have the player 1, when initializing the game, send over the seed, and then use that seed on multiple different you know, random number generators. Again, you only need these 3 with a few different values. I'm not going to do it entirely, but assuming you have a bigger number than 7, because 7 isn't like again, once you figure out the sequence, it's going to be easy to, you know, figure out how to create the code every time. But let's say you have a bit of a bigger number, you can use this bigger number in the code that you send. Remember, everyone is on the same page, so everyone should get the same randomized number from this counter, provided they have the same seed, which they do. So if they have the same seed, you can roll a random number each turn on everyone's systems. Have this random number be hidden, not be used for anything really. You roll it, then the player who has their turn rolls the dice, they get, I don't know, 3, and they need to send a code. They don't just send 3, they send 3 plus the random number that they rolled, the hidden random number. You can still use the base 7 logic, it's fine, as long as, remember, this random number is probably going to be bigger than 7, so if you have multiple data, keep this as the last digit, so that you don't have to worry about data afterwards. But yeah, you'd send over both the rolled dice value and the random number. So once you send the code over, people are going to put the code, decode it, and instead of checking for the checksum, they're going to have their dice roll, and then over here, ignore these two for a moment, over here they're going to have a random number. So then they're going to check if that random number is equal to the one they rolled. If they are equal, then it's fine. That means that yes, you are on the same page, you did roll that number, I'm going to advance the game as it should. If they're not equal, it's not going to accept the code. It's going to say, hey, this is you got something wrong over here, because that's not the same number that I have here, you see? So, okay, these are a few ways you can use this setup. So again, you can use these random numbers for turn order sequences, for checksums, not really checksums, but like checking whether a code is correct or not each turn. And of course, since it's called a pseudo-random number generator, you can use it to generate somewhat random numbers for events in your game, and have them all happen in the same order on every player's system, so everyone is actually synchronized. Hopefully this was, you know, a good overview of what's going on. I don't know why everything is missing over here. Did I delete a bunch of stuff? I want these back, thank you. Okay, I'm going to tidy up this code a little bit, add the comments, and then I'm going to well, I'm going to share the code. It's probably going to be right here on screen. I'm not going to put it on gbgShop because it's not even a game. But yeah, I'll have the code on screen if you want to check it out. It's going to be tidier than this. It's going to have comments. It's going to have a little bit of explanation. You can just check it to see if you missed anything. And yeah, I hope this was useful, and I'm looking forward to your GBG Shop Jam games. So yeah, thank you for watching, and happy building!